Hi, my name is Mohammad Ahmedov. In this video lecture, we are going to discuss a couple of examples on evaluating the integration using so-called Riemann sum. So let's first of all understand what is the Riemann sum. In a previous lecture, we discussed, hey, if we would like to figure out the area under some curve y is equal to the f of x, in this case, x in the square, we would like to split this into the small rectangles. The widths of the rectangles are going to be the same. So it is going to depend on the number of the rectangles. So if you are given the interval from A to the B, then, and if the number of the rectangles is equal to the n, then the width of the rectangle delta x is going to be equal to b minus a, the width of the whole interval, divided to the n, which is the number of the rectangles. So this width here is going to be equal to the delta x. So this is delta x, this is delta x, this is delta x, and so on. Well, in order to find the heights of those rectangles, we need to know the y-coordinates of these points. So essentially, let me denote this point to be equal to the x1, this is going to be x0. So essentially, A is going to be equal to the x0, and B is equal to the xn. So then this point is going to be x2, x3, x4, x5, x6, and so on. So the coordinates of this point is going to be equal to the fx1 and f of x1. And the height of this first rectangle here, the height of this rectangle here is going to be equal to the f of x1. The height of the second rectangle is going to be f of x2. The height of the third rectangle is f of x3. And the height of the last rectangle here is going to be f of xn. And every time if we would like to figure out the area of those rectangles, we need to simply multiply the heights. Oops. We need to always multiply the height into the width. So in general, we are given those points. We call them the sample points, x0, x1, x2, and so on, xn. And how we find them is essentially, so we are going to simply add the delta x as the previous ones. So the x0 plus delta x is going to give you x1. Then x1 plus delta x is going to give you x2. Well, if you substitute x1 to here, it's going to be x0 plus 2 delta x, right? And so on, xn is going to be equal to the x0 plus n delta x. Well, the area is going to be equal to, now, the summation of, so the area is going to be equal to the summation of delta x, which is the width of those rectangles, times the height of those rectangles, which is equal to the f of xi, right? Where I goes from 1 to the n, and if you take its limit when n goes to the infinity, it's going to be equal to the area. And this sum here is going to be called as the Riemann sum. Well, in the next example, we are going to evaluate the integration, or this is going to be the same as the integration of the f of x from A to the B. Well, in the next example, we are going to evaluate the integration using the Riemann sum, and we will try to also figure out the limits. So in order to evaluate the limits, we need to know a couple of rules. So the first rule is going to be the summation of the I. So what is the summation of the I when I goes from 1 to the n? Which is simply the sum of the numbers from 1, 2, 3, 4, and so on, n. And the sum is going to be equal to the n times the n plus 1 divided to the 2. Well, that's a formula. And also, we need to know what is going to be the sum of the I goes from 1 to the n of the I in the cube, which is going to be 1 in the cube plus 2 in the cube plus 3 in the cube plus and so on plus n in the cube. So it appears that it's going to be equal to the n times the n plus 1 divided to the 2 in the square. Well, we need these two formulas in order to evaluate the limits. So now let's do an example. Let's say we need to evaluate the integration of x cubed minus 6x dx from 0 to the 3. Okay, so first of all, we need to evaluate this integration by summation of the delta x times the f of xi, where I goes from 1 to the n, and when n is going to be fixed, so n is going to be equal to the 6, for example. And in the second case, we are going to find the limit of the sum. I goes from 1 to the n, delta x, f of xi. Okay, then we will figure out what is going to be the summation when n approaches the infinity. So let's start from the first case. So in the first case, we are given the a to be equal to the 0, b to be equal to the 3, n to be equal to the 6. So that's why the delta x is going to be equal to b minus a divided to the n, which is equal to the 0.5. Well, now we are going to find all of the sample points. So the x0 is going to be equal to the 0. x1 is equal to the 0 plus delta x, which is 1 over 2. x2 is going to be equal to the 1, right? I just need to always add 0.5, where delta x is the previous sample points. So x3 is going to be equal to the 1.5. x4 is equal to the 2. x5 is equal to the 2.5. And x6 is going to be equal to the 3. So what we need to do is we need to evaluate the area to be approximately equal to the summation of delta x times the f of xi, right? Where I goes from 1 to the 6. So well, it is going to be equal to. So let me take out the delta x from the brackets. So it's going to be delta x times the f of x x1, which is 1 over 2, plus delta x times to the f of x2, which is 1, plus 3 over 2, plus n plus f of 3. So we are going to just put those values into the definition of the function. And if you remember, our function used to be x cubed minus 6x. So we need to validate this function into all of the 6 sample points. There's going to be delta x times 2. So if you substitute 1 over 2, is going to be equal to minus 2.875. So if you substitute 1 to here, it's going to be 1 minus 6, it's going to be minus 5. So if you substitute 1.5, it's going to be minus 5.625. If you substitute 2, it's going to be equal to the minus 4. 2.5 is going to be 0.625. And if you substitute 3, it's going to be 3 in the cube minus 18, which is equal to the 9. Well, if you multiply this to the delta x, which is 1 over 2, what we get is minus 3.9375. Well, it appears the integration can be negative as well. And it is not actually the area as its physical meaning. It's like it's going to be the net area. So I'm going to explain you what does it mean in a moment. So this function here, y f of x is equal to the x cubed minus 6x, is roughly going to look like this. So what we did is we split this area under this curve and over this curve into the 6 rectangles, and we found the area of those 6 rectangles. And this area, the net area, is going to be negative because if your curve is below the x-axis, this integration is going to be negative. Integration is negative. And this integration is going to be positive if your curve is above the x-axis. So the integration of your curve from A, let's say, until B here is going to give you the net area. So the negative area is going to be subtracted from the positive area. So or summed. So you just need to sum these two areas. And this value, minus 3.9375, is going to be the net area. So the integration, please remember the integration is the net area. So which is very similar to something which is called like a net profit, right? So you basically get some income, and you have some expenses, and if you just subtract the expenses from the incomes, you are going to get the net profit. So this is the same for the integration. So now what we would like to do is we would like to figure out exact area by taking the limit of the sum when n goes to infinity. So let's try to do this. So the number 2, so what we are going to do is we are going to find the limit of the sum I goes from 1 to the n, delta x of f of x I. So let's figure out the general formula of the f of x I. So x I is going to be delta x, x0 plus delta x times the z I. Okay, where the x0 in our case is equal to the 0 and xn is equal to the 3. Because if you remember, we still need to integrate the function x cubed minus 6x dx from 0 to the 3. So this is going to be equal to this sum when n goes to infinity. So let's just substitute this now to here. So well, simply this is going to be I times the delta x because x0 is equal to the 0. And also that the delta x is going to be equal to 3 over n, right? Because it's going to be 3 minus 0 over n. So xi is going to be equal to the 3 over n times the I it appears. So let's substitute this. So this is going to be the summation of 3 divided to the n times the f of 3I divided to the n. I goes from 1 to the n. So I'm going to substitute this to here. So f of x is equal to the x cubed minus 6x. It's going to be the summation of 3 divided to the n times to the 3I divided to the n in the cube minus 6 times to the 3I divided to the n. So this is the f of x, right? I goes from 1 to the n still. So we still need to find the limit. So the limit of the, so let me take out some of the terms out of the sum. So here it's going to be a summation I goes from 1 to the n. So here we have, so 3 in a cube is 27 times to the 3, it's going to be 81 divided to, so n in the cube is going to be n cubed multiplied to the to this n, it's going to be n in the power of 4, right? So this is multiplied to, so this is multiplied to I in the cube. Okay, so minus, so let me write this down as a separate limit because we can split the limit into the two pieces. So minus times, so 3 times is a 6 times is a 3, it is going to be equal to 54 divided as the n in the square times to the I, right? So this is what we have. And here what we can do is we can write this down as like the limit of 81 times the n in the power of 4 times the summation of the I cube, I goes from 1 to the n, and minus the limit of n goes to the infinity of 54 times the n in the square times the summation of, so I forgot the summation here, summation of the I goes from 1 to the n. And if you remember in the beginning, I gave you the formula how to find the summation of the I from 1 to the n. It is n times the n plus 1 divided to the 2. While the summation of the I in the cube, it's going to be n times the n plus 1 divided to the 2 in the square. Well, if we are going to obviously substitute this to here. So let's substitute. What we get is it's going to be the limit of n goes to infinity. So the 81 divided to the n in the power of 4 times to the n in the square plus n divided to the 2 in the square minus the limit of 54 divided to the n in the square times to the n in the square plus n divided to the 2. Okay, so let's evaluate this limit. So 81 times is the limit of, so this n in the power of 4 can go inside this bracket as the n square. So it's going to be n in the square plus n divided to the 2n in the square minus the limit of, so let me take out 54 out of 2, so 27 out of the brackets. It's going to be the limit of n goes to the infinity, n in the square plus n divided to the 2n in the square. So let's evaluate these limits. So this limit here is going to be the limit of, so I think I can do this like this. So it's going to be 1 over 2, right? Plus 1 divided to the 2n. Okay? So when n goes to the in the square, when n goes to the infinity, the second term here just vanishes. So it goes to the 0. So that's why we simply have here 1 over 4. Okay? So at the same time here, so this is going to be equal to the limit is going to be equal to, so 1 divided to the 2 plus 1 divided to the 2n. And again, the second term is going to vanish when n goes to the 0, so this is going to be equal to the 1 over 2. So now I'm just going to substitute this to here. It's going to be 81 times the 1 over 4 minus 27 times the 1 over 2. And if you take out the 27 out of the brackets, can we do this? Yeah, 27, it's going to be 3 over 4 minus 2 over 4. Well, it's going to be 27 times the 1 over 4, which is equal to, I think it should be minus. We probably made a mistake somewhere. Oh yeah. So it's, let me write this one more time. So if you take out the 27 out of the brackets, what we have here is 3 over 4 minus 1 over 4, which is like 2 over 4. Okay, I think I made a mistake here because I already deleted this 2 to the 54. So 54 divided to the 2 is equal to the 27. So that's why its limit is equal to the 1 simply, right? So here it's going to be equal to 1, and the second term is going to be equal to the, yeah, sorry. So it's going to be 81 over 4 minus 27. If you take out 27 out of the brackets, it's going to be 3 over 4 minus 1, which is equal to the minus 27 times the 1 over 4, which is going to be roughly equal to the minus 6.75, or not exactly equal to the 6.75. Well, we evaluated the integration exactly. So from 0 to the 3x cubed minus 6x dx is going to be equal to the limit of the sum delta x f of xi. I goes from 1 to the n. When n approaches the 0, infinity, sorry, it's going to be minus 6.75 exactly. And at the same time, we evaluated this integration approximately by taking only 6 terms. I goes from 1 to the 6th, delta x times the f of xi, and in that case it was equal to, so this is going to be approximately equal to this one, approximately, and that integration we evaluated as the minus 3.9375. So what's the conclusion here is, the first conclusion is integration can be negative, integration can be negative, right? So in order to evaluate the integration exactly, we need to find the limit, right? So as n goes to the infinity, we get precise result. And the most important one is, so we can't really afford to do all of these calculations every time when we need to evaluate the integration. So the third conclusion would be we need to figure out a way how to evaluate integration without the Riemann sum. Without the Riemann sum. Well, in our next video lecture, we are going to discuss how we can evaluate integration without the Riemann sum. Thank you very much. I hope that this was helpful for you.